how much can we really understand the human brain? It's a big mystery still. It's just a bunch of electrical signals going on, and we can't really interpret it very well in terms of just doing this. It seems so simple to all of us. All of us can do it, but somehow, for some reason, we just have no idea how it's being processed in here, and then the command is sent to do this. What I do is to integrate the field of neuroscience and the robotics together and call it a field neurobotics. And in the field of neurobotics, what we do is to use robots to understand, rehabilitate, assist, and enhance humans' neural control of movement, which is in general how the brain controls our motion. So what I would really like to do is, given that my research area can have impact on disabled people, I would love to start a non-profit organization, or even just maybe for profit, to get the robots out there for people who would benefit using it. Just they don't currently have them available to them, and it would be great to have a way for me to get it out there through some tangential meaning than just my research and teaching. 10 years from now, I would like to look back and say, because of this exposure, now this field is richer than then 10 years, 10 years ago.
To this presentation, MacArthur Fellows who are changing the world. My name is Peter MacDougall, and it was my privilege to serve as the president of Santa Barbara City College from 1981 to 2002. 21 challenging and rewarding years of working with SBCC's exceptional faculty, staff, and board of trustees with the shared objective of developing an outstanding community college. It is a thrill to be back on campus for this most auspicious occasion. I sincerely thank Superintendent President Dr. Andrea Servin for inviting me to provide a welcome for an event that has such significance to the Santa Barbara City College community. Santa Barbara City College identifies 1909 as the year it was founded. On this, the cusp of the centennial year, I can think of no event that could provide greater validation of the college's past and the potential future value than today's celebration. Our educational systems at all levels exist because of the fundamental belief that through a system open to all, the potential of individuals and our collective potential as a society will best be realized. When we review the achievements of today's presenters and the substantial societal benefits resulting from their work, one could legitimately ask, could there be a more vivid validation of this belief in education? Certainly today, the SBC community basks in the glow of the excellence and notable achievements of our two former students. Now retired Professors Michael Mallon, Jim Jolka, Mike in mathematics, Jim in chemistry, and current faculty members such as Dr. Larry Friesen in bioscience and others still teaching at SBCC, I'm sure are pleased and proud to have played a part in the rigorous academic journey and success of today's presenters. I hope and expect that for Dr. Belcher and Dr. Mutsioka, today's visit rekindles many positive memories of the years at SBCC, and specifically how those years on this very special campus may have contributed to the confidence and originality reflected in their nationally, if not world-renowned, academic achievements. Dr. Serban will be introducing our returning alums. As mentioned earlier, it is my privilege to provide a welcome, and I will do so. Welcome to Santa Barbara City College's exceptional faculty who deliver on the promise of college through your daily work with students. I am confident you will be reinvigorated by today's presentation and how it exemplifies the impact you may have on the lives of your students. Welcome to the SBCC trustees, administrators, staff, and friends and donors of Santa Barbara City College, who in very substantial ways support and encourage that margin of excellence for which Santa Barbara City College is known. Welcome to our reason for being, current Santa Barbara City College students, who I believe will be inspired by knowing the two individuals who are today sharing the brilliance of their achievements with us, once occupied the classrooms you are now fortunate to be in. And finally, welcome to Drs. Belcher and Matsuoka, whose individual and collective achievements so forcefully validate the highest potential of our educational systems. Thank you, and Dr. Serban.
Thank you, Dr. McDougall, for such a warm and great welcome message. And I would also like to recognize President Emeritus John Romo, who has joined us. I thought he was there. I would also like to welcome you all to this very special event. Our guests this afternoon are truly exceptional, and I'm honored to introduce them to you. Dr. Angela Belcher is Professor of Material Science and Engineering and Bioengineering at the Massachusetts Institute of Technology. She was named a MacArthur Fellow in 2004. Angela, whose research has earned her numerous national awards and recognition, is a leader in the innovative field of nanotechnology. And there is a particular reason why Angela chose this field. She's a vegetarian, and she wanted a field that involved no animals. So what better field than nanotechnology? One of the most visible of Angela's honors was being featured on the cover of Forbes magazine in July 2001. She appeared in the forefront of the photo, followed by a lineup of 4 other experts in the field of nanotechnology, one more renowned than other. Gerd Binning, Nobel Prize winner for development of the scanning tunneling microscope, Stanley Williams of Hewlett-Packard, Mark Reed of Yale University, and Harold Craighead of Cornell University. The year before the Forbes article appeared, Angela was one of 30 scientists nationwide to be honored by President Clinton at the White House with the Presidential Early Career Award for Science and Engineering. In August 2002, the American Chemical Society named her one of the 12 women who will have the greatest impact on chemistry in this century. Dr. Yoki Matsuoka is Associate Professor of Computer Science and Engineering at the University of Washington in Seattle. She was named a MacArthur Fellow in 2007. She's one of the leading pioneers in the emerging field of neurorobotics, a discipline that merges neuroscience with robotics. The caliber of her research has won Yoki national recognition, including the 2004 Presidential Early Career Award for Scientists and Engineers, the highest honor bestowed by the American government upon upcoming scientists. She was also named as the Anna Loomis McCandless Faculty Chair in 2004. She has presented her research at national conferences, and recently she was featured in a television segment on Nova Science, now on PBS. Besides their brilliance and tremendous accomplishments, Angela and Yoki have a few other things in common. Both wanted early on in their lives to become professional tennis players. They would have probably made more money. Both went through the rigorous discipline of the sport and both suffered from tennis injuries. And while Angela never won at Wimbledon as she wanted, she selected another great goal to win a Nobel Prize, which I'm sure she will. Yoki played tennis for SBCC and was selected Scholar of the Year for the State of California Community Colleges in 1991. Her trophy, a large metal plaque, is in display case in the gym. We are holding on to it. It may save the college from this budget crisis later on. Yoki took a scientific interest in her injuries. She became a mechanical engineer, neuroscientist, bioengineer, robotics expert, and computer scientist all in one. Angela and Yoki are both mothers of very young children. When Yoki was informed about her MacArthur Award, she was nursing her new baby, her son, who is now 1 year old, one of her 3 children. Some of us can barely take care of ourselves, let alone achieve so much and have 3 kids. Angela is the proud mother of her son, Braz. Angela's innovation and creativity in various scientific fields has been evident since her days as a straight-A student at Santa Barbara State College. She was on the President's Honor Roll for all 4 of her semesters at SBCC between 86 and 88, finishing with a GPA of 4.0. She was the winner of the prestigious President's Scholarship, the Organic Chemistry Award, and Biological Science Award. Yoki was also an almost straight-A student. It is hard to understand why she got a C in American government and politics, and I'm going to check who that instructor was. She was really upset about the C, but in spite of that, she liked the college so much that she encouraged her own mom to be a student here a few years after she attended SBCC. And her mom was an international student and F1 visa, and Yoki is almost international, but we didn't charge her our international student fees because she became a permanent resident by the time. Yoki, too, was on the President's Honor Roll for all 4 of her semesters at SBCC between 1989 and 1991. We believe our college has had a significant impact on Angela and Yoki, and anyone holding a different opinion, please keep it to yourself. If Angela had never attended SBCC, she would have been for sure tremendously successful anywhere else, but likely in some other area. Her invention and development of the Belcher technique of using viruses as builders would likely not exist. Her virus work started at UCSB on a strong science and math foundation received at our college. If Yoki had never attended SBCC, it is perhaps unlikely that the robotic hand directly controlled by the brain would be as advanced as it is today. It is certainly no doubt that great mentors and faculty had contributed to Angela's and Yoki's exceptional success. And although there are many individuals who should be individually recognized, I would like to take a moment to recognize James Holka, SBCC Professor Emeritus of Chemistry, and Michael Mallon, Professor Emeritus of Mathematics, who are with us today. And Jim and Mike, would you just please stand up for a second and be recognized? One of our greatest satisfaction of college presidents is to brag about the success of our students, and we do that constantly. In 2002, Peter nominated Angela for the Distinguished Alumni Award given by the Community College League of California, an award Angela won. I nominated Yoki this year, and I would like to present to her this certificate of recognition for her outstanding achievement, which is signed by Scott Lay, President and CEO of the Community College League of California. Along with a red SBCC bag of even higher value. And because we thought neither Angela nor Yoki would want or have room in their offices for one more trophy, We are dedicating to each of them the very first 2 tiles in the brand new Hall of Fame for distinguished SBCC alumni on the Alumni Plaza by the bookstore. This way, they will be a perennial presence on our campus and inspiration for many of generations to come. At the end of the program, I would like to invite you all to join us for a reception in front of the theater to greet and celebrate the success that both Angela and Yoki have achieved, and in recognition of how proud we are to name them our own. We will also have towards the end some time for questions, so without further ado, I'm inviting Angela to the microphone.
Well, I'm very choked up. I'm very happy to be here, very honored to be here to help celebrate the centennial and to speak to my former teachers and the great students here at SBCC. I do have to make a comment about the Nobel Prize that I mentioned. I don't really know how that got out, but I put it in a scholarship application because I thought the committee, who would reject someone who said that one day they were going to win the Nobel Prize, because so I didn't really have that aspiration, so I just thought it would be too hard to turn down, and I actually did get that, so might be a good technique to use. But it really was here that I fell in love with science, and it's often quoted that one day I really fell in love with molecules, and that's completely true. It's really driven a lot of what I do. I fell in love with the idea of large molecules and in solution and interacting with their environment, and it's really driven a lot of most of all the science and engineering that we do currently in my lab. So I'm very grateful to the faculty members. Jim Holka really encouraged me in freshman chemistry, and I remember really struggling on batteries. Do you remember that, Jim? You remember everything. And now I'm considered a battery expert, and so I really appreciate that. And Gary, I was sitting in an organic chemistry seminar. It was yesterday, and I was on the edge of my seat. I was so excited about the reactions that I was looking at, and I was thinking about you. So again, I really appreciate all the support that I had. So in order not to get choked up anymore, I'm going to head straight into science here and tell you a little bit about what I've been thinking about since I left here several years ago. What my lab is really interested in. So I run a lab at MIT of about 25 people that are PhD students and postdocs and then undergraduates. And the main focus of our research is understanding how nature makes materials and borrowing those ideas to work on what we like to say nature hasn't had the opportunity to work with yet. And I'll talk about some of the applications that we're working on. So I called this From Nature and Back Again, Giving New Life to Energy, Electronics, and the Environment. So it really is the interface of many different disciplines: chemistry, material science, biology, biological engineering. And we like to think about the interface between these disciplines because a lot of our work is based on how abalones grow shells. And these are red abalone that were found right off the coast of Santa Barbara. And I'll talk a little bit about abalone as a material. But an abalone doesn't think, oh, I'm a chemist, I'm going to build it this way. I'm a biologist, I'm going to build it this way. It's what do I have in my environment to make the best material for my function? And that's what we're interested in doing. And I'll tell you a little bit about how we think about this. The main thing that my research group is interested in is we call it genetic control of materials. Again, here's an abalone shell. An abalone shell is a biocomposite material. It's 98% by mass calcium carbonate, 2% by mass protein, yet it has really many exquisite properties. It's 3,000 times tougher than its geological counterpart. It's made in ocean temperatures and ocean pressures without adding toxic materials back into the environment. We think that's an incredible design idea. Let's make something in a non-toxic way. So a lot of our work is based on that. But something that's more interesting to us is when a male and a female abalone get together, they make millions of offspring. They pass on to that offspring the genetic information that says, this is how to build an exquisite nanomaterial. And so that's what we're interested in. Diatoms, too, which are made out of glass, SiO2. So this is glass that's made in the ocean. And they also pass on their genetic information. This is how to make glass, but this is how to make glass in a really specific three-dimensional structure. And every time they pass on this genetic information, you get another exquisite structure at the nanoscale. And so what we focus on is, can you give genetic information to a solar cell, or can you give genetic information to a battery so that it has a code that says, this is how to make a battery. And so it can assemble itself. And can it have the possibility of evolution where the battery can get better as a function of time? And that's some of what I'm going to talk about. So when we think about future technologies, we start about 4.5 billion years ago to the beginning of Earth. It only took about a billion years to have the first life. And it was, this was organisms that were replicating, eventually have organisms that were photosynthetic. But it wasn't until about 500 million years ago, during this time period called the Cambrian geological time period, where there was an explosion of life, and our organisms started making hard materials. So before this time, they were already doing really tough things: photosynthesis, life, replication. Why weren't they making hard materials? That's what we wanted to know. And so the answer is pretty much opportunity, that it was during this geological time period there was increased calcium and silicon and other inorganic materials in the ocean. And now all of a sudden they had this pressure to take these ions and make them non-toxic, and they started building hard structures. And so through evolution, it was about 500 million years ago that abalone started making shells, but it took them about 50 million years to get good at it. So most of the graduate students in my lab are there for about 5 years. And so we started thinking about how do you come up with a rapid way of trying to get organisms to make solar cells or batteries. And that's what I'm going to talk about a little bit today. And I should say that my first company that I founded was named Cambrios Technology. It's named after the Cambrian geological time period. My second company is called Siluria Technology. So all my companies now are named after geological time periods. And they're so long that there's always something significant that happens during that time. So I should point out my favorite biomaterial. This is my son, Brazos. I gave him the genetic information that says this is how to build bones, this is how to build teeth. But anyone that has had a 2-year-old know they're very complex organisms. And I should say he's standing next to his favorite biomaterial, which is the Triceratops. So we started thinking about what is a simple organism that you can use to start getting it to use a new toolbox to make materials that are important to me. And so we started working with viruses and bacteria and now yeast, trying to genetically engineer them to have a new function, build a battery, assemble a battery. And this is just you probably don't see very many of these here, a snowflake. One of the things that's interesting about snowflakes is they're self-assembling systems. So there's a nucleus at the center of an ice crystal that forms this really exquisite structure. And so what we're looking for are nucleuses that are nuclei that you can have that don't build a snowflake but can start self-assembling electronics. So if you have the right information, can you start assembling interesting electronic materials under biological conditions? And so a couple of years ago, I was asked to give a talk in Washington about what I thought the biggest challenges in material science are. And I took this very seriously, and it was a couple of years ago now, and I put it together. I said, I like a material that's self-assembling. I like a material that's self-correcting and self-healing, one that grows its own template, recycles its own template, and only grows to desired length and diameter and stops. I'd like to only use environmentally benign precursors and solvents, room temperature and pressure, and generate little waste. And so when I gave this talk several years ago, there was starting to be giggles in the audience, and these are really people that were much more powerful than me and professionals, and they said, wow, that's a pretty big, long laundry list. Why don't you just pick one thing? But if you think about it, biology's already accomplished all of these things and how it makes materials. And so that's what we're focusing on, is giving biology the opportunity to work with the rest of the periodic table. So organisms like eukaryotic cells, which could be yeast to humans, or bacteria cells, what we want to do is actually convince them to use a new toolkit to start building materials that are interesting, electronic materials. So this is the reaction vessel where life came from. It's the ocean. These are some of the ions and atoms and molecules that are in the ocean. And we think life did a pretty good job. We think biomaterials, humans, abalone shells are pretty good. But we think that life could have done better if it had more opportunity. It had this opportunity 500 million years ago. Let's give it the opportunity again. And so let's see what it can do. Here's some natural biomaterials. This is a coccolithophorid. It's a unicellular algae made out of calcium carbonate. This is a 1 micron scale bar here. This is an abalone shell that if you cleave this and you look at an electron micrograph, you'll see it's actually made out of these little tablets, these nanostructured tablets of calcium carbonate that stack on top of each other to form this brick wall-like structure. This is from an undergraduate project that I worked on diatoms made out of SiO2. And there's magnetotactic bacteria that have small single-domain magnets that are used in navigation. So all of these are made in ocean temperatures using non-toxic precursors. This is just showing you what an abalone shell looks like, a little bit higher magnification. There's an organic matrix in between here. So the organic matrix is actually key to controlling the nanostructure, and it's key to making a really exquisite material. And so only 2% by mass, but this is the difference. This 2% by mass is the difference between an abalone shell and chalk. And you can take chalk and easily snap it between your hands, but abalone shells are actually quite difficult. Well, the key are proteins. The proteins that are actually involved in growing these materials. And many of you know that there's basically 20 amino acids, and these amino acids that make up proteins differ from each other based on their chemical functionalities. And it's these chemical functionalities that are the whole key to controlling calcium carbonate, controlling silicon, controlling bones. And that's what we decided to look at. So here's a kind of a mechanism of how a shell grows. There's this thing that looks kind of like a birthday cake is 2 calcium carbonate tablets that are nucleated and controlled by these little squiggles, which are proteins. The combination of these proteins actually help the tablets grow through these organic matrix layers that look like this. This is a tip of a growing pearl, actually, where the length of the diameter of these tablets haven't grown out to the full extent yet. But this is the mechanism by which biology uses to grow inorganic materials. Now again, if you want to think about how to make things on the nanoscale, so on the scale of a billionth of a meter, why don't you start with things that are already really, really small? Why don't you use a toolkit of things that are really small? And so this is actually just showing you a scale structure. This is about 100 nanometers, across. This is about the size of some of the current electronics in your computer and in your cell phone. And this is DNA and proteins showing you how much smaller they are than your current electronics. And so our idea was start with things that are really small and convince them to start growing and assembling useful materials for electronics. So again, going back to the periodic table, nature has chosen calcium in the form of calcium carbonate and calcium phosphate, silicon in the form of silica, and some iron, Fe2O3 or Fe3O4, but really hasn't worked with this part of the periodic table or this part of the periodic table. It's hard for me not to throw out questions because that's the way I teach. But no quizzes today. But you know from your undergraduate biology classes that transition metals are really, really important in biology, but they're usually as single atoms or maybe a really small cluster. You don't see them as inorganic crystals. So biology has the ability to work with that part of the periodic table, but hasn't chosen to do so for larger structures. So the idea is that in an abalone shell, for example, there's a protein matrix that has alternating negative charges that come from carboxylic acid groups. Those negative charges can grab calcium out of solution in the ocean and start putting down a layer of calcium and then carbonate, calcium and carbonate. So it acts as a nucleation point to start growing materials. And so what we decided to do was, what if you take any generic protein with any generic inorganic material and put these together? Can you find a protein that matches anything on the periodic table they're interested in, and then use it to grow something useful? And so the idea comes from, goes back to the vegetarian point, was that everyone knows that you have antibodies in your body, and antibodies are really specific for small molecules and proteins that they can recognize and bind to. And we wanted to use those millions of years of evolution and combine them with man-made fabrication to come up with something we called evolved hybrid materials. So it really is in the interface between living and non-living. How do you give living things the ability to start growing non-living structures? And so when we first started thinking about this, again, we said, how do you find the right molecule to meet that interface? It took about 50 million years for biology to do this. So we need a rapid approach. We need to do 1 billion experiments at a time. 1 billion experiments at a time is kind of hard. And so it's a process called combinatorial chemistry. How many people have heard of combinatorial chemistry? Basically, it's a way of doing lots of different combinations at once and trying to basically find the one that meets the particular kind of requirement that you're looking for. Now, one way of doing this is actually through DNA engineering, which we're going to talk a little bit about. But so DNA is pretty inexpensive. Proteins is much more expensive. So instead of going through and making 1 billion different proteins and testing that, we're going to do this at the genetic level because doing genetic engineering is a lot easier. So when we first started thinking about this, we decided to use a bacteriophage, a kind of virus. Bacteriophage are viruses that only infect bacteria. They have single-stranded DNA. It's very simple. We have high school students in the lab always come in and can work with these particular kind of viruses. These are completely non-toxic to humans and are actually FDA approved and used in medical diagnostics. Bacteriophage are also sprayed on your lunch meat. Not our bacteriophages, but to reduce actually bad bacteria making you sick. So we can actually go in and take this single-stranded DNA, and through just using simple genetic engineering, we can actually cut and paste it and add a random DNA sequence to our virus. Now this virus is a very simple structure. It has this DNA, and it actually is made out of a protein coat. So by going in, this DNA codes for this protein. By going in and making genetic modifications in its DNA, it actually makes modifications in the protein on the surface of the virus. So yellow gene here, yellow protein. Now you can do this 1 billion times and get 1 billion viruses that are all genetically identical to each other, but they're going to differ just based on their tips, their chemical functionality. Now we're going to use that as a library. So when you have 1 billion different molecules, you call it a library. And we're going to take our 1 billion different viruses. In about a 1 microliter sample, you can put 1 billion viruses. So you can take them, and now you can force them to interact with any kind of materials you want them to interact with. This could be a semiconductor used in your computer chip. It could be magnetic materials. It could be materials for solar. And now what you ask these viruses to do is say, can any of these viruses learn to interact with this material that it's never had the opportunity to work with yet? Okay? Of those 1 billion possibilities, you'll have a couple of them that will find a chemical match for this surface, for this particular kind of material. All the ones, see this one's falling off, all the ones that didn't match get washed away. Anything that actually could bind to that surface, we keep that. Now we infect it into its bacterial host, and now the bacterial makes 1 million copies of this particular virus. We call it a clone. And so now we have this factory, this bacterial factory, make millions of copies for us, and now we force them to interact with that same material again. It's kind of a Darwinian process, survival of the fittest. Of these 1 billion, which is the very, very best for interacting with my material of interest? And so my students can do that in about 2 weeks. They can find a winner for lots of different kinds of materials. Here's the current applications that we're looking at in my lab. Batteries is a big area that we work in, basically virus-based batteries. We work in an area called electrochromic devices. These are simple displays, a couple of color displays that could be used for things like smart cards for credit cards. We work in solar cells. We work in very high efficiency solar cells, and we work in very inexpensive spray-on solar cells. We work in catalysis in the area of water splitting. How do you take sunlight and water and turn it into hydrogen for fuel? We work in fuel cells also for energy applications. We work in fibers for incorporating batteries into textiles for soldiers' uniforms. We work in nanoelectronics, medical diagnostics for colon cancer and breast cancer detection, and we work in carbon capture and sequestration. This is a project where we're using another organism, yeast, not viruses, to capture CO2 from a coal plant and convert it into calcium carbonate for building supplies. It's all done through genetic engineering, training the organism to learn how to take CO2 and turn it into something useful. It can be done in the order of a couple of weeks. So these are the major topics. I've never been accused of being focused. So this is a genetic toolkit that you actually just go in and you make simple modifications. You can go in and do cut and paste and make modifications in this gene called gene 3, and that'll make modifications in this end of a virus here. You can go and make modifications in this gene called gene 8, and that expresses actually 2,700 copies of a protein on the coat of a virus. So it's a virus as a genetic toolkit to grow materials. Now, another thing that's nice about this organism, this virus, is that it's actually 1 micron in length and about 6 nanometers in diameter. And every time it replicates itself, it's always exactly the same length. I tried to be a polymer chemist for a couple of weeks as a postdoc, and I wasn't very good at it. And one of the reasons is you go and you make these synthetic organic polymers, and they come in lots of different lengths, and then you actually have to go through and figure out how to size separate it and get them all out. And I didn't really have the patience for that. But in this case, biology likes to give you things in exact units. If you have a protein in your body and it's too short, has a mutation in it, it can lead to disease and all kinds of problems. So why not exploit this, something called monodispersity of biological organisms? And so I'll tell you a couple of stories depending on what time I have. This is an idea of a student of mine, and as you guys are thinking about going to graduate school, it's always good to apply for your own fellowships, because when you go into graduate school with your own money, it gives you a lot more flexibility. So this is a really brilliant student of mine. His name's Asher, and he came in with his own money. He wanted to see if he could use a virus to find very rare events in a semiconductor, and I'll tell you about using it for something more useful in a minute. And he's a really smart student, graduated #1 in his class at Berkeley. And I said, it sounds like a good idea, but I don't think it's going to work. So good luck. Give it a try, and we'll see how it works. And so here's this idea that when you grow two different materials where the atoms are spaced differently on top of each other, and you grow them right on top of each other, this will make sense to you from other ideas. There's a mismatch in the stacking of those atoms, and that mismatch in the stacking of the atoms actually leads to an atomic level defect, an atom that's in the wrong place, basically, and that can lead to all kinds of problems. This is one reason why LEDs are expensive. It's one reason why very high efficiency solar cells aren't more efficient than they are, because in order to get the broadest range of light collection out of solar cells, a lot of times you need to put a lot of different kinds of materials together. Okay, that can lead to problems. So his idea was take something that you knew had some defects in it, train a virus to bind this defect, not bind a perfect surface, bind the defect, not bind the perfect surface, back and forth. This is why I said, kind of good luck, give it 6 months and see what happens. And he was able to pull out 2 out of a billion sequences that could recognize atomic level defects in a semiconductor. And I'm like, oh yeah, I knew that would work. And so then he took a fluorescent tag and he added it to these materials, and so now he can actually go and, like, when a wafer comes off the fab line, he can count the number of defects by just looking at the fluorescent signal. And that was kind of neat, and this is him, he got a good job and went on, and it was kind of neat. But we started thinking about larger materials. What about airplane engine blocks? What about when you take an airplane material, it's a super alloy material, wings and engine blocks are, and when they go through fatigue damage and they get pushed back and forth, it leads to cracks. Well, the chemistry of a crack is slightly different than the chemistry of the surrounding. And just like an antibody can recognize some slight difference in something that's in your body, you can train viruses and yeast to find small cracks in airplane engine blocks. We're actually working with several large companies now in airplane engine blocks and in large-scale equipment for oil drilling to train organisms to find and sit on a defect and give off a signal. Okay, and so that's kind of where Asher's work ended up going. So from the very, very small scale to the very big scale. Well, that was actually really fun, but what we really wanted to do was train organisms to grow materials. And so this is a cartoon of what a virus would look like if it could grow 4 different little semiconductors, electronic materials, on its tip. And this is a transmission electron micrograph. It's a 1 micron length scale here of a virus that's actually grown 4 or 5 semiconductors on its head. This is a pretty high resolution image. This is a little bit higher resolution, and this is a little bit higher resolution over here. So this is actually, I think, around 800,000 times magnified. Can you guys see those stripes, dark light there? Those are atomic lattices in a crystal. And so these viruses have been trained to template a material, and then you give it a semiconductor precursor, just zinc and sulfide in solution, and it grows a semiconductor particle on its head. And so we thought that was really, really cool. We published it in a high-impact journal, but I don't think it's really changed the world technology. And then we started thinking about viruses themselves, how they're always the exact same length. And we started going through and engineering not the tips to grow materials, but the whole body to grow materials. Because, as a material scientist, this isn't a virus, this is a wire. And can we get it to actually grow electronic material for a wire? And so we could. This is actually a virus that's been engineered to grow silver nanowires here. They're all grown at room temperature. You pour in the silver, they grow the material for you, all done at room temperature. There's actually no reducing agent for those chemists in the group as well. But you can also give a virus multiple genes to grow multiple materials. This is a virus that we engineered to grow 2 different semiconductors side by side, zinc sulfide and cad sulfide. So once it has the right genetic information, all you have to do is give it the precursors, and it grows you this hybrid semiconductor material. Definitely very, very fun. So this is actually showing, this is a virus that's growing multiple kinds of materials. This is an an elemental map showing zinc and cadmium, showing you that it's actually growing these materials. You guys probably don't have an atomic force microscope here yet. Is that right? You guys should get one. Basically, atomic force microscopy is a way of looking at structures and even DNA at very high resolution without having to look in a high resolution transmission electron microscope. So you guys don't have a high resolution transmission electron microscope. The one we use is about $1.5 million, and it's actually not good enough. And so, but these atomic force microscopes work by actually having it's like a record player needle with a really sharp tip that can bounce along the surface of DNA or on the surface of a semiconductor or anything you actually stick under there. And it's interacting with the surface. Say you have this DNA underneath it. These are chromosomes. And there's a laser that goes and hits the surface and bounces off to a detector. And so what it allows you to do is look at things at really small scale. Basically, that they can be wet, they can be dry, but you don't have to do special preparation for them. And so I'm just going to show you these kind of images in case you've never looked at atomic force microscopy images. These are two students of mine that they've both graduated now. Yu Wang is a professor at UCLA. Cheng Yi is at Johnson & Johnson. Their idea was to engineer a virus to stick to a gold electrode, cross the gold electrode, and then have a gene to grow gold or silver or some kind of electronic material in between to make a little nanowire, basically nano electrode. And so they did that very successfully. They gave it the gene, it grew it. I'll show you this. This is atomic force microscopy image here, these colored images. And it had pretty good electrical properties. But again, this is not the change the world technology. This is one virus crossing an electrode. We wanted to build devices. And I'll spend the rest of the time, if I have 5 minutes, this is going to be rapid, the rest of the time talking about batteries. So we've been engineering viruses to make lithium-ion batteries. You guys are all probably using lithium-ion batteries right now in your cell phones and your laptops. You probably know about exploding virus. I'm sorry, not virus. Our virus batteries don't explode. Sorry. About exploding batteries. But there's all kinds of things that are important: storage capacity, energy density, power density, rate capability involved in batteries. So in batteries, you have two different electrodes: a negative electrode and a positive electrode. We'll talk a little bit more about it in a minute. But about 75% of the mass of the battery that you have in your cell phone right now is wasted space and wasted mass. One of the things that's important in a battery is something called energy density, how much energy you can store in a certain amount of space. And so getting rid of that wasted space is important. So we started think about biology. Think about how DNA is packaged in the nucleus of your cells, how efficiently it's packed in there, tightly packed in there. Can we use biology to start thinking about how to redesign batteries? Okay, so here's a negative electrode. The negative electrode that you have right now in your cell phones is graphite. The positive electrode you have right now is something called lithium cobalt oxide. It's one of those materials that does explode at times, at bad times. And then you have these lithium ions. So this is a way of going from chemical energy to electrical energy. You have these ions that actually go back and forth between these structures, and that's how these batteries are working. Lithium ions, positive electrode, going back in and basically storing and retrieving energy. So my students decided, well, let's take M13, let's take this virus, and get it to grow an electrode material. We're going to use cobalt oxide, a metal oxide electrode. Let's use self-assembly, have a virus self-assemble itself, and then let's use additional evolution to see if it can become better and better and better. And that's one thing that I really like about biology, is that if you can get it to do something at all, even if you get a crummy electrode material or a crummy battery material at all, you have the power of evolution on your side. So even if it's bad, it can get better and better and better if you can train it and give it that opportunity. And so that's been really, really fun for us. So this is my students' first battery. They made this in a shaker in the lab. Just basically, it had to be 37 degrees to grow the virus. And then they actually were able to pull out little single virus electrodes that are going to be used for a battery electrode here. And in case you've never built a battery before, you have to have something that is a way of getting the electrons out. You have things that are called current collectors in and out. So this is copper. We actually got a virus to grow cobalt oxide electrode material at room temperature, and then we put electrolyte in between, and we put lithium on top. So I'm not expecting you to be battery experts, but I'll show you some real battery data anyway. This is a graph. This axis over here is specific capacity. This is related to the amount of energy that you can store from your battery electrode. And this is cycle. So you know that your rechargeable batteries have to charge, discharge, charge, discharge. You want that to happen fast. and you want it to go all the way up in terms of what its maximum capacity is, and you'd like it to happen for at least hundreds of times, right? You're going to be mad if you charge and discharge your iPhone 5 times and then you need a new one. So this is actually data. This is your commercially available batteries right now in terms of what its energy, what its specific capacity is. It's right around here, around 300. This is a theory of what we thought our materials would be able to reach, and this is actual real data. So we reach theory, and it starts to fade as you charge and discharge. So we're really excited, less excited, less excited. But at least we're better than commercially available batteries. And we actually got about 2 times better than commercially available batteries our first try out, or at least the first try my students told me about. And so then my students decided, well, let's go in and let's engineer this virus to be better. Okay, it worked pretty well, but how good can you get it to be? And again, this is a lot of battery detailed information, and it's probably even beyond the scope of first-year chemistry. But again, thinking about how you have those 2 electrodes and how those lithium atoms are going back and forth between those 2 electrodes, that's ionic conductivity. These are going back and forth by using a plus charge going between these. But in order to be a good battery electrode, you need to be a good ionic conductor and a good electrical conductor. Okay? And so what my students decided to do is go and give a virus 2 genes, one to be a good ionic conductor and one to be a good electrical conductor. And they re-engineered it. And then what they did, these are actually transmission electron microscope images. This is a virus in high resolution, this is 50 nanometer length scale, where it has 2 genes, one to grow gold, one to grow cobalt oxide. We give it gold, and it starts growing gold. But you see all the spaces in between. It's not a perfect wire. All those spaces in between is where it has the sequences to grow the good ionic conductor. Now we add the cobalt in solution, and it fills in all the spaces, and now you have a new material. It's a cobalt oxide gold. It's a good ionic conductor and a good electrical conductor. And we go and we test this material as a battery electrode material. Again, this is our first try. So here's commercial available down here. Here's our first try. Here's our second try. And it actually lasts much, much longer. It's stable much, much longer. I probably have like a minute left here. So we wanted to be able to show how these could self-assemble. And so I worked with Professor Paula Hammond at MIT to make something called weak polymer electrolytes. These are a solution of something that's positive and a solution that's something that's negative. That's basically an organic molecule. And what she does is she actually takes a glass slide, sticks it in positive, sticks it in negative, sticks it in positive, sticks it in negative. And what it does is it makes this nice layer, film, of positive and negative on top of each other. Now that can actually be used to hold the electrolyte in your battery. So what kind of image is this? Atomic force microscopy image. We engineered our viruses like her electrode polymer, and now they actually all stack on top of each other. Now you give it cobalt, and it zips up and grows the structure here. That's a cobalt oxide battery structure. And so here's the process. Take a slide, dip in polymer, dip in virus, dip in the battery material, and you pull out this battery that's transparent, and it's about almost 3 times better than commercially available batteries. And my students stopped giving it to me because it is transparent, and I drop it, and it's actually really hard to find. It's actually like saran wrap. It has some pretty good mechanical properties to it. So it's a self-assembled, room temperature grown, virus-based battery. Here's another picture of it here. Now, because I'm out of time, I should say we spent a lot of time making cathode materials, and just in the last couple of weeks, we've been able to engineer 3 genes in a virus now to make really extraordinary batteries that can go for hundreds and hundreds of cycles at almost full capacity, using a material called amorphous iron phosphate that people started looking at years ago and have discounted it because it wasn't good enough. But through genetic engineering, 3 genes, we've been able to get it something that's actually that's as good as some of the best batteries that people are looking at now for like the Chevy Volt and batteries that could be used for plug-in hybrids. So the same technology can be applied to solar cells, has been applied to solar cells, and all other kinds of things. I'm out of time. I'd love to take questions at the end, and I'd like to thank you for your attention.
All right, while my slides are being set up, it's actually interesting to hear Angela's students stop giving this clear thing because she breaks it or loses it. I think there's something about that as I walk into the lab and none of the demos work. And students swear that they were working until the moment I walked in. And when I was a grad student or undergrad, I used to always say, like, is there something about those,
important people, and then all the demos stopped working. So we somehow achieved that goal. So that's a sign when things don't work around you, you might be pretty important. So you should be aware. So this MacArthur thing, I was going to even start with telling you about it. So, maybe you're thinking there's something you're going to achieve in your lifetime that's going to make you famous. And then I've also wanted to be famous in some way. But MacArthur thing, the genius thing, okay, maybe fame comes with it, maybe. So one of the things that happened, I don't know if it has happened to you, but I was sitting in the airport recently to go to give a talk in Cleveland, and I was with my son and then dressed up in the crappy clothes, and then 2 guys were staring at me, and I thought, oh boy, I have some slobby things on me, I should just hide somewhere. And then one of the guys come over and says, excuse me, are you the certified genius? I said, I guess so. And then he just yells across to his buddy and says, hey, she's the one, she's the genius one. So then they come over and start talking, and then lots of people start coming and talking, and then we have to get on board. And then once we were on board, the seatbelt sign went ting and came off. People actually lined up in an aisle to ask me questions. And I thought, wow, I finally achieved this status of this famous thing. This is how it must be like to be a rock star. But the questions were kind of funny. The questions were mostly about, oh, I have this big concern. I think my son is a genius. And I really would like to know what he should be doing. He's only 4 years old. But should he be taking some math classes? What should he be doing? So it's really interesting to know that, a lot of people, this genius thing is, overrated. But it's in all of us. And it's in, every definition. And I think it's really fun that sometimes you just get exposed to those things. Do I have to keep cracking jokes?
Yes.
All right. What else do I have in my sleeves? Well, I can actually start by talking about my days at City College. I went to a local school called Dunn School up in the valley over. I decided that I really wanted to play college-level tennis. And this was an excellent place to do it. And that's really first why I arrived to Santa Barbara City College. As I started pursuing my tennis, I have come to realize that my body might not be made for tennis. I was always kind of half broken, my knees and my back, and I was very famous in being in a physical therapy office. And to the point that I thought maybe I should pursue sports medicine. But at the same time, I thought, okay, maybe there's something else I have to pursue besides tennis in my life. And I thought, wow, this place, City College, they offer amazing classes. I really should take more of those classes and see what I can do. So that's really where I started. I thought, well, in high school, I really liked things like, oh, great, look at that. That's my title. So work hard, play hard. I think that's the way to go. And I also sort of listed in my affiliations because this is sort of part of, my life was at City College. I could not decide what I wanted to do. And I thought that if I decide on one thing, then my life would be set. If I majored in math, then I'm going to be a mathematician. And I was so afraid that I just went everywhere, and I think I even have a slide in that. Oh, here we go. See, me on the Santa Barbara City College tennis court playing tennis. This was actually from the newspaper the Santa Barbara City College had. I just pulled out and scanned it. But if you look carefully, I'm wrapped around in tape everywhere. Yeah, and I have even picture of another one I should really scan is a picture of me being treated on the physical therapy table, and then 2 people are treating me and wrapping me, and I'm doing my homework. So that's another one. But anyway, so that's where I started, and then I initially thought, I want to do math, and I thought, well, actually math here is amazing, right? Math here, of course, Mike was an amazing teacher, but beyond that, this is better than UCSB. I took classes at UCSB, and then those classes were huge, and here you got personal attention, and I learned so much. But I thought, do I really want to be a mathematician all my life? And I thought, no, I want to do apply math. I want to apply math to do something like calculate the traffic flow and figure out how much to tilt the highway. I thought that'd be really cool. But then I thought, I really like physical things. I want to do physics. Then I thought, no, I want to do something more practical like nutrition. Then I thought, I don't know, maybe I want to do pre-med. I got as close to about here to there for a cadaver in the Santa Barbara City College before I decided that I'm not going to do pre-med. Then I finally found this thing called engineering. And that kind of hit me, and I thought, wow, engineering is kind of fun. It's like takes all those things that I just wanted to do, like math and physics and, even some science, and then I get to actually do something applied. So once I settled on engineering, I went to talk to a bunch of counselors here and said, engineering seems to come in different flavors, like mechanical and electrical, and which one do I do? And, I sort of started browsing all those things. And then they said, well, mechanical engineering, you get to sort of play with mechanical stuff. I said, all right. And electrical stuff, you get to actually put, wires and then conduct current and, and computers, you just sit in a terminal and program a lot. And I thought, wow, that's kind of a weird description, so I'm not sure which one to go into. So I pretty much tossed a coin and then I applied to all different colleges with different majors and ended up majoring in electrical engineering and computer science at Berkeley. Turns out, oh, no, before that I should tell you about this one. So, Santa Barbara City College has this thing called Minority Engineering Club. There are a bunch of non-minority people, so even if you're not minority, you should join it. It was really, really cool. So you go to this meeting, and the counselors are there, and the students are there. You have great discussions about how to become engineers, and there are great mentors who tell you what to do. And then we got to go to job fairs and got to party, and then that was really fun. And this job fair I went to in LA with a bunch of people from this, I got a job at Apple Computer. And that was really, really good. And then that was my first experience that I really got. And then because of all this experience at Santa Barbara City College, and Apple Computer was a stepping stone. Then I went to UC Berkeley, and then I majored in electrical engineering and computer science. And that was just the right thing for me, because I finally realized that what I wanted to do in my life was to connect tennis, something that I thought I wanted to do all my life, to this engineering part. And this is what I really wanted to build, a tennis buddy for myself. So this is something that I've drawn up a long time ago and thought, well, tennis, if you play any individual sports, you know that when you play, your opponent better be about the same level as you, or else if they're really much not as good as you, then it's really boring, and if they're much better, they're probably bored. So I thought it would be, if I had this tennis player and I could turn the knob depending on which day it is, it would be really awesome. Some days I'm tired, I just want to beat somebody really badly, and maybe I'll turn all those things down. And some days I want to be challenged, and then maybe I can turn all those things up. So I wanted to build this, and then I asked around and says, well, how do I go about building this robotic-like thing? And then I met some professors and started joining a lab, building robotic legs as an undergrad. And I wanted to keep going. This was it. This is really what made me happy. So I went to this place called MIT, kept majoring in electrical engineering and computer science, and this is what I built there. And this robot was called COG. It stands for cognition. It's supposed to achieve a 2-year level cognition by spending 5 years of graduate student time. We never quite got there. It's like 15 years later, it's still not there. But it's gotten pretty good. So I've actually built the arms and hands, and then I was exploring in different environment. And I thought the way to go is to start from, just really from scratch. Where when we're born, we have reflexes and sort of motivation. So reflex, babies, when you go and touch their hand curl around, I hardwired those into this robotic program. And then legs go if you something scratch on the back, for example. And then everything else was done in neural networks, where the computer and the robot actually learn to do the right thing. And that's how we operate too. We do things wrong, and then we learn from those experiences, and then we try to do the right thing the next time around. So from just having the robot learning the environment, just trying to experiment with different objects, this robot became to a point it was good enough to grab almost anything in the lab. But it could grab anything, but it couldn't manipulate objects. We seem to have this crazy, amazing hands that we can manipulate any objects in very delicate ways. And we claim that we're better than monkeys because we have those things, right? But we couldn't do that in this robot. We could not provide that dexterous human ability in the robot. And at that point, I realized that, I can't keep pursuing this artificial intelligence or computer science or engineering, whatever it's called. I really have to learn more about the biology and neuroscience. So halfway through my PhD, I just decided, I'm not going to do electrical engineering anymore. I'm going to do this thing called computational neuroscience. So that's what I ended up doing for my PhD. And if you looked at my thesis, it looks like a neuroscientist thesis. But you know what? That was a really great experience. And I thought I'd come back after learning everything about neuroscience and then fix all the robotic problems in the world. But you know what? Neuroscience really captivated me, and it still has captivated me, and that has really formed my research area. And you know, there are so many people in the world who have neurological disorders. You know, stroke. Something like 800,000 people get stroke every year, and there are about 6 million people who are around with disabilities, permanent disabilities. There are almost 1 million people who have spinal cord injury, so their neck broke at some point and they can't control the rest of their body. This is just a number within the US. And it turns out, as I was thinking about it, I said, you know, those people can really be helped by some robotic technology that I already know. So rather than helping the robotic technology by knowing neuroscience, why don't we combine it the other way around, which is to help the neurological disorders using the robotic technology that we already know. So that's the direction I ended up going, and I went to this place called Harvard for a postdoc, and then now I ended up in the University of Washington. And I created this field called neurobotics. And this is really, as you can tell from it's a fusion of two words, neuroscience and robotics. And I work on really the row, that's really the intersection part. And the moment I say the word neurobotics, a lot of people imagine something like what's on this left-hand side. Maybe this is a laser. Here you go. So really, when I combine the neuro and robotics, people immediately say, oh, so the robotics must be the limbs, and then the neuro must be the brain, and the brain is naturally controlling the limbs. It's true, something I do. This is one of the projects that I'm involved in. But at the same time, I also want you to, in the future, as you walk around in the world and think about the word neurobotics, I want you to also imagine there are robots that you simply interact. Sitting on the table or somewhere in the environment, person goes over and touch it. The moment it touches, just this non-invasive communication allows the robot to know what brain state that you might be in, and the robot would act accordingly and push you in the right way. And now it's a closed-loop communication between your brain signals and the motion, and the robot would also learn to correct its own motion. So we can do things like stroke rehabilitation using stationary robot that's not embedded as part of their body. That's also part of neurobotics. And turns out the visualization in neurobotics was done really well in the 70s already, and this is probably, for many of you, it's way too young for this, but this was Star Wars, and then when Luke Skywalker lost the hand fighting against Darth Vader, he got this neurobotics hand, which looks just like his hand, but it's inside its own mechanical system, and as he's thinking about moving his own hand, all those mechanical systems moving inside. Turns out, this is exactly what I'm trying to achieve. And I didn't even have to make my own video. I just violated the copyrights. I got one of my grad students to rent the video and made this clip. So that's really the idea. You know, again, natural brain signal. We don't think anything when we do this. But this is so hard. We can't get robots to do this at all using our neural signals. When we extract everything about our brain signal, we still can't decode what that signal allows us to do this. So it's really complicated. So I figured I'll give you a 1-minute anatomy course so that you can even sort of understand a little bit more about what I'm talking about in terms of integrating neuroscience and robotics. So in terms of the anatomy, and then specifically neuroscience, in the brain, it's all current, electricity going around. And that allows you to think like, I'm thirsty. Maybe I want to reach out for a little glass of water. That signal gets propagated in electricity to the spinal cord. That's like a little tail out of your brain in your spine. And that comes out of the spine and becomes those nerves, still sending current, arrives at the muscle. Muscle has this amazing ability to take those current and then use calcium and potassium and those things that you should eat bananas for, and then turns that muscle current into force, positional displacement, and things like stiffness changes of the limb. And those muscles affect the joints, and then finally affect the behavior. So I wanted to grab for water. All of that, I thought about it in a current, and then gets propagated to the muscles. Muscles convert that into actual work, and then finally to task and behavior. So that's how humans work. But it turns out, we're going to not worry about the feedback part, even though we have tons of sensory feedback. But I wanted to quickly go into the robotic 1-minute course. So after this, you're going to be an expert in robots. But the structure is quite similar. Robots, well, instead of the brain and the spinal cord, we have a computer. Everything in there is current. It learns. It has pre-structures. It's very similar. Instead of nerves, we have wires. Instead of muscles, we have motors. We have metallic joints. And really, in a way, the structure is quite similar. So now you can start to imagine that if the human body parts in some places are broken, maybe we can start thinking about replacing that with the robotic parts. And that's exactly what the field of neurobotics can be like. So going back to this human structure, let's assume that your friend unfortunately had a car accident and they have had major local trauma. Lost, most of the inside is intact, but the limb is gone. In that case, as I've shown you, you can actually place a robotic arm and then connect it back to the nerves that you used to have. And then that's exactly this project is about. This project is courtesy of Rehabilitation Institute of Chicago. Now there are about 25 people like this walking around in the U.S. who have had the surgery called a nerve reinnervation, where they took the original the nerves that used to go to the arm, that the arm is no longer there, and they're just floating. And the neurosurgeon goes in and rewire those things onto the chest muscle. Then, whenever that person thinks about moving the original thumb that they don't have anymore, the chest muscle actually twitch. Then you can go and retrieve that signal from the skin and then control the robotic device. Robotic device actually, again, is controlled by the current. So those currents that's arriving to the muscle, if you can extract that and then move the robot, that's great. So that's exactly how those people are operating their limbs. And here's a video of one of the guys using it. It's pretty good. He can move multiple joints simultaneously. He has about 4 joints or so in the arm, and then hand can open and close. And whoops, hold on. Technology. Okay, that's all I wanted to say here. So this technology, so all those things are just coming up right now. Even though in the movie we've shown that this was going to be available in the 70s, there's huge hype in the 80s with the RoboCop and all those things, but really, finally, this is becoming available in the last 3 to 5 years. But the resolution's limited. There are only about 4 joints that we can move at the same time. Hand has 22 degrees of freedom. This is a very, very complicated system. There's no way we can somehow get that signal out right now. And also, this technology only works for people who just lost the limbs and have everything else intact. But as I said, there are a lot of people in the world who have injuries in the brain or in the spinal cord, and we can't address that issue. So what if we have that problem? What if the spinal cord injury occurred? Healthy brain, but there's no way to propagate information, so they're paralyzed from spinal cord down. We can actually build a robotic device that's wearable. That's something that we built in our lab. And then, instead of going through the spinal cord, now we go through an external computer and wires and then send the movement that was commanded from the brain to the robotic device by bypassing their nervous system. So that's what we do. And how do we actually tap into the brain signals? So this is a company out in Connecticut called the Cyberkinetics. They have a technology, they sell this commercially now, to embed actually electronics in the brain surface, really inside, and then push some small needles into the system and the brain. It records electricity from the brain, goes through the external wire. There's a little plug that comes in from the skull, and then goes to the computer. And for this specific video, what this guy can do is by thinking about moving the cursor up and down and side to side, that thought can transform into cursor movement on a computer. And this is extremely useful for people who are so paralyzed to the point that they can't even blink to indicate their intention. There are a lot of people like that out there. So this allows them to press maybe yes and no on the computer. Are you hungry? Are you in pain? All those essential things that they couldn't say anything about because they could not indicate that even though they have this healthy brain inside. Now with this technology, we can actually get those expressions out. We can even display, say, keyboard on the computer screen. Lots of things can happen. But turns out, again, this is also very, very early on in technology. We need actually Angela's help to get this working. But the brain doesn't like having those foreign things inside and ends up rejecting it over time. So it ends up floating around. So we only had 2 subjects so far who's gone through this trial, and there are infection issues and so forth. So for my research, my collaborators are people who have monkeys. Unfortunately, we work with monkeys, and it's not a vegetarian thing. I'm not a vegetarian either. But I don't work with monkeys because I think they're pretty cute. But I work with people who, enough said. Okay, so here's a guy who has monkeys, and we can now go into their brain signals And we have extracted the signal and then poured it onto the robotic device. So what we did was train the monkey to reach for food that's placed in the different places. And then we strapped his arms under, and then we put a robotic device, and then used the same brain signal that was used to reach out for food using his own arm, and to control this robotic device. So this is a monkey thinking about wanting to reach for that food. We used the electricity coming from his brain directly onto controlling this robotic arm, reaching out for food, and he can eat it. Okay, so this is the level of technology that we can do now. We can control the robotic endpoint in a 3D to go to where he intends to go. What is primitive here and what's actually faked here is the hand. So this robotic hand that opens when then closes to grab the food, graduate students sitting there with a remote control to make that happen. We just couldn't get that signal from the brain at this point. Okay, that video is kind of cute. And we also want to pay attention. Now we're going to go into smaller sort of detail of the fascination of this hand. But even for building this prosthetic hand is really hard. So those people are typically given something that might look like a hand, but either it doesn't move at all, but it just opens and closes. Again, we're not providing this human-level dexterity that we're talking about. And sad enough, even those are built so poorly to the point that the moment they're done with these experiments, when they go home, they go right back into using a hook. That's how bad they are right now. So we got to fix that problem somehow. And roboticists have been trying to fix that problem for about 25 years now. The roboticists, including myself, many of those actually I was involved in constructing myself, not the really early on one, but they have 5 fingers, all the right joints, and this has been going on. The only difference that probably is between what was built in 1983 and 2006 are how big the controllers are in the back. These moved really, really slow, required about 2 refrigerators worth of controller electronics. This one actually can be done with electronics that could probably fit in the forearm. So things are improving, but still, if you ask this hand to, maybe flip through some pen and do some dexterous operations, it still can't do it. And one of the things that seems to be missing from the field of robotics is an inspiration from biology in the right way. Biology doesn't mean 5 fingers and the right joints, but there are a whole lot more that are in our hand. For example, if you look at this one, this is a very clear example. The palm is rigid. And if you actually look back and even look at like the NASA hand all the way and everything else, the palm is rigid. Come on, have you tried to do anything with a rigid palm? You can't do anything. But all this really, really incredible smart robotics people have gotten together for the last 25 years, and the only thing they built were the robotic hands with the rigid palm. But there's a good reason for that. When you start to compromise and figure out what you can do with the current technology, palm is such a great place to put electronics or motors or anything like that. So they end up compromising on those things. But they don't know for sure if that's a good thing to compromise. And I have to say that's not a good thing to compromise, because humans cannot operate with their rigid palm. So we sort of dove into, as a big our lab, to really pursue what the human-level dexterity is. Really try to understand what those biomechanical hardware is and what's the software that's controlling it is like. And then once we understand it, maybe we can start to build the robotic device, and then start to augment some injured people. So this is our first attempt done in 2001. We actually couldn't even find enough information in the literature. So we dissected lots of human hands to get all the parameters that we wanted, and then built this robotic hand over here with a couple of hand surgeons. It performed really well. It did far better than any other robotic hands, to the point that it was in a museum typing keyboards 8 hours a day for 6 weeks. But interestingly, at the end of 6 weeks, we had to keep tweaking the parameters that goes into it, and the robotic hand kept getting harder and harder to operate. And then we got hand surgeons to come to the museum and have a little evaluation. And he said, "I'm sorry to tell you this, but your robotic hand has developed arthritis." So turns out if you overuse the robotic system, arthritis occur, and because there's no cell replacement, it just gets more and more rigid and eventually just not going to move anymore. So we learned quite a lot by building this device, that certain things we can mimic and certain things we cannot mimic. So we're still in the process of learning exactly what we should mimic, but for the last 6 years, we iterated on different designs of fingers, and finally we reached this point. This was just taken this summer, we finally assembled what we feel is really happy, a functional, anatomical robotic hand. And it looks quite biological, and then you can see in this motion, I should have shown you other robotic finger movements first, but it's quite biological looking. It can be driven by the human motion itself, as you can see here, or it can be driven by the muscle, the electric signals from the brain that arrives at the muscles that control the finger to also control this robotic finger now. Okay, so it's very biological. We're pretty happy with it. It's difficult to show you all fingers moving together because we don't have that video yet. Hopefully next time. So really, to get there, we had to actually make more biological discoveries. Even though we're contributing to the field of robotics, turns out most of the journal publications happen to be in the science. So we've made discoveries. Actually, how much time do I have?
About
7 minutes. Okay, I'll tell you sort of different things that we've discovered in our lab so far. So one thing we found out was this complicated routing of tendons in your hand. If you shouldn't do this at home, but if you peel the skin off from your hand, you'll see this very, very complex web of tendons in your hand. It's been modeled, but very poorly so far. We've tried to find out, do we really have to mimic all this complicated structure? Maybe it's just an evolutionary garbage. Maybe if mimicking those would be a bad idea. It's just too much work. Maybe we can actually find out certain things that we just can extract. So we ran computer simulations, hardware simulations to find out which links and which sort of tendon connections that we can cut out. Unfortunately, it seems like so far the answer has been leaning to the fact that it's an evolutionary marvel. It seems that all those little connections seems to make a lot of sense. Index finger, actually, it can move with 6 muscles. If you try to build a robotic finger that does not have this complicated structure, it's going to require 8 motors to do it. So we somehow became pretty efficient in using only 6 muscles to do all this index finger motion. So there's something very nice about this geometry. We also found out that by having this complicated structure, some of the muscles are used for dual purposes. For that reason, even if you start from the same posture and then have exactly the same current commands coming to the muscles, but if they come in different orders, turns out you end up with different postures. So the timing also matters in terms of the neural signals. The moment we actually mimic this tendon routing and structures, we unfortunately, we also figured out that the cylindrical bone structure, which was much easier to build, was not good enough anymore. Humans have this really complicated bumpy surface on the bones, and we thought that it was just some sort of byproduct of the way the bone is built. But turns out we take advantage of those bumps and grooves. For example, one thing that we found out was that this figure doesn't necessarily show you maybe, but we found out that we're actually naturally strongest in grabbing objects than pushing the finger to push something like a bead sideways. And that function comes purely from the shape of your bone. It's not that you've been training to be stronger in a grabbing direction. That's not what it is. It's actually from the shape of the bones. So by finding out all those facts, unfortunately, we had to machine all those bumpy, groovy bones. And if you've ever tried to use any like CAD or fast prototypes to build bumpy surfaces, those things are so hard. We actually had to spend one staff. I paid him like $80,000 for 2 years just to come up with one set of hand bones that we could use. So it was a very expensive finding in science. And finally, we also wanted to, now we are starting to find a lot of biomechanical or hardware information, but we also were starting to find out a lot about the neural signal, the software part that goes into the hardware. You know that there are billions of neurons in the brain. Those cells all fire and then have lots of currents coming and then eventually somehow ends up in this one behavior. And indeed, we have many different ways to do, say, for example, I'm doing this. I could be doing this in a variety of different ways for my brain to do it. So it's called a redundant control structure. I could have chosen many different ways to do it. That means that, but still, biology somehow picked one solution, one specific way of doing this. Those specific set of neurons fired. So we went back and trying to find out why certain neurons fired and not the other ones. And the way to find out was what's called optimization. We wanted to know if you had a lot of choice to do something, and if you picked one solution, you were optimizing on something. So we thought that maybe if you want to do this many, many times, maybe the brain chooses a structure that's most energy efficient, for example. So we ran some simulation and actually found out that we're not minimizing on the energy. And then we kept running more simulations. And what we found out is that we seem to be somehow optimizing on utilizing as many small muscles as possible and as little of the big muscles as possible whenever we're doing things. I know it doesn't necessarily make sense, and it doesn't make sense for us either. Because if you didn't know anything about muscles, and if you were told that big muscles produce a lot of force, small muscle produces little force, and big muscles have, and then if you combine all those things and then control a limb, maybe you want to use the big muscle a lot. But turns out we do the opposite. And that's something that we actually published and then we hypothesized that when we run with our legs, where energy matters a lot, when big muscles firing a lot, legs might use big muscles more. But for hand tasks, when we manipulate objects, precision makes far more sense than to try to save energy doing the tasks in the hand. So for legs, we found out that people use bigger muscles more often. For hands, we tend to maximize on the utilization of the small muscles. So maybe we actually have one of those as more like a fine-tuning buttons. So that's so far what we found in terms of the neurocontrol structure. So, and we now are extracting signal from actual people's brain to control our robotic device. Not only from the muscle signals, the currents that arrives to the muscles, but actually the current that exists in the brain. And to do it with the humans without having the infection problems is to simply drill the hole in the bone. That part is easy. Take the bone part off. Then the brain has skin on it. Peel the skin off. But don't go into the actual tissue. Just put electrode right on the surface of the brain. That actually doesn't cause a whole lot of infections. It's actually something that's done routinely for people who have epilepsy. So if you have anybody who has seizure all the time, eventually what they do is that they go into the hospital, put these electrodes on the surface of the brain, sit in the hospital for 4 days or 14 days until they have a seizure, and then those sensors actually detect where the center of the seizure was and then go in and do the operation. Operation mainly means take out that part of the brain. But usually those people are sitting in a hospital with all kinds of great brain information pouring out for no reason. So we actually, whenever those epilepsy patients come into the hospital and then they have the sensor grid embedded onto the brain, we come into their hospital room with a cart full of robots and say, excuse me, can we do an experiment with your brain signals? And then we try to get those free brain signals that's pouring out and correlating with the behavior and see how we can use them. So we're starting to really use the neural signal to control this great biomechanical, anatomically correct robotic fingers. I just told you about this pretty narrow area of the neurobotics, but I just wanted to pop you back up to the field, sort of global neurobotics field. This is just sample of what's going on in my lab alone. So I told you about sort of the prosthetics and brain-machine interface and the anatomical robotic model and how that can help. But we did quite a lot of extensive work also on wearable robotic device. How do we build them? How do we make them light? And then once we have those systems, how do we use the signals to control them? For people who have spinal cord injuries, healthy brain signals, how can we actually bypass them? We also do, as I said, the stationary robotic device to do stroke rehabilitation. Can we come up with a better paradigm? Because now the robot knows exactly what brain state you might be in. And then doing actual biofeedback based on that. And then through that process, of course, we're discovering more and more about the human body. What's interesting is that through neurobotics, turns out all the things I've said, like making scientific discovery, rehab, are obvious, but turns out we're getting funding for a variety of different reasons. For example, what we do can also lead to disease prevention and prediction. By having a person coming and sitting in front of the robot and playing a video game and measuring their precise motion, turns out can allow us to detect an onset of certain disease way earlier than a clinical onset or detection. So there's a disease called Huntington's disease, which is similar to Parkinson's disease. turns out we can detect the onset of their disease up to 7 years prior to the clinical onset using a robotic device. Let's see, what are other interesting ones? Space exploration. We want to send those dexterous robotic hands to Mars and flipping rocks to see if we see bugs underneath it. And currently, we don't have any devices that can do that. So we send humans, well, not on Mars yet, but we send humans for 5 minutes at a time, expose them to radiation and all those things because they're so much more dexterous than any robots out there. But we can start to do that. So NASA is quite interested in doing this. Computer graphics. You see all those, Bugs Life and all those movies, and then those animations get more and more human-like in motions. We're actually contributing a lot to that. The more we understand how humans move and how the biomechanics, how the neural signal work, those things contribute to those little figures to move much better. So there are a lot of interesting things that come out of neurobotics. Finally, I also wanted to tell you that neurobotics turns out to be great for outreach, and it seems that Angela does quite a lot of the outreach also. But we think it's very important to try to recruit more women and younger people to get excited about these fields. So what we do is that we combine engineering undergraduate students, these days even high school students, and then women especially, to come to our lab and meet. We pick one disabled child, and that kid usually has some wish list, and then I ask the kid and says, well, if Santa Claus was an engineer, what are the 10 things that you really want from Santa Claus this winter? And they come up with a list. And about 8 of those things are completely impossible to build. And 2 of those things, something that we can imagine building with a team of pre-engineers. So we go in and build those things. And that builds a really nice sort of bonding experience for everybody. And then that allows more people to pursue engineering and then increase the number of women in the field. Also, turns out high school students and undergrads have been publishing journal papers out of our lab because of these efforts. So that's really exciting. This is the final slide with pictures. Everything I just talked about seems really far-fetched from the point of view of time. The question Mike Mallon asked me earlier was like, so when can we start using your hand? And who's going to be wearing it first kind of questions. I do my research in such a way that I try to reach out and try to solve problems that's, going to be sort of the solutions that will be available in about 25 years' time. But, I also want to affect society today. And it seems that there are things that we can do to affect society. And then there are 4 quadrants of ways that I try to affect society today. And these are done through 2 companies that I've started. So one is really providing the robotic assistance now. Those things might not be publishable, but as I said, through outreach and so forth, we were able to make difference in people's life with the robotic technology. Through that, we are also trying to recruit more students and girls. This is, again, maybe we all do this, but cheap way to include our family photo with our dog named Jalapeno. And now that we're living this crazy life of raising kids and doing engineering and then starting companies and all those things all at the same time, I realized that this is really hard. This is why women don't pursue this field. But can we actually, now that we know from this end how difficult it is, can we actually solve some of the problems so that more women can enter it? I actually have a company that allows that process to become easier, but not only that, I also try to help people who have chosen to just become full-time mothers to get back into the system. And finally, through all of this, I'm trying to provide lifelong learning opportunities for elderlies. As the population is growing older, people want to keep learning. People want to keep contributing to the society in some way. And again, through some mechanism that one of the companies I have, we provide those opportunities and learning environment and the ways for them to provide to the society. So if you're interested in learning more, those are my web pages. And thank you very much.
Wow, this was so fascinating. I could have stayed here for hours. So next time we'll book you for 20 hours. It's so fascinating. We have a little time for a few questions. There are 2 microphones here if you'd like to come to one of them, if anybody dares to ask anything.
I mean, it's very interesting that the VA is putting in, and DARPA are also putting in quite a lot of money now. And you might have heard of a project called Revolutionizing Prosthetics. DARPA has just put in almost $40 million just to build an upper limb prosthetic device for people who are coming back from Iraq. And the statistics is quite different these days. After apparently World War II, there are more people who came back dead than came back with a paralyzed. But now it's the other way around. Modern medicine has helped people to come back alive, but with permanent disabilities. So definitely there's a growing field in that. Still, from the VA's point of view, their current technology is to provide a hook that's as comfortable as possible. But that is changing, and then hopefully we're contributing and changing that. But it's still a very slow-moving field at this moment.
You've both paid credit to teachers you've had in the past. I'm interested in how mentoring really encourages people to go their own pathways. So I wonder if both of you would talk about whether you met someone who really acted as a mentor for you in terms of taking ownership of where you wanted to go with your science.
So I've had so many outstanding mentors, and I just feel completely blessed that way with mentors from here and UCSB as well as in business. And you know very well one of my mentors, Evelyn Hu, who was my postdoctoral mentor, and I'm on the phone with her almost and I have 2 companies with her, on the phone with her almost every week. She still guides me and mentors me. So I've been very, very lucky, and I also have a group of about 25 people, and then work with between hundreds to 1,000 K through 12 students a year, and I mean, if I hadn't had these really incredible mentors, I wouldn't be where I am today. And so I strive to try to give that, to try to even be somewhat of a mentor. It's hard to be compared to Evelyn Hu, but back to other people. And so it not only has the great mentorship helped me get to where I am today, but it always presses me to be a better and better mentor, knowing what other people's time has given me. And like I said, I just feel incredibly blessed. And one of the most touching experiences I ever have are when, from students I had as freshmen or high school students I had years ago still send me letters all the time. I decided to go in this field because of you. Thank you for the time that you've given me. And I get tens of those a year, and that means more to me than any kind of award, knowing that you've really had a positive influence in a young person's life or career. So it feels more rewarding for me than maybe it was for them. But.
Yeah. I think, there are sort of 2 questions, like what mentoring has really affected us the most? And then to me is sort of the encouragement. And, all of us feel insecure about us, right? And, at times you feel like, I'm not really, really good at this, so I might just not do it. And those are the times that I think mentoring is extremely helpful to say, no, we believe in you, go, 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 go. I think that really helps. So I think, even people who, as a mentor, you might think are not, doing so well, I think there are ways you can find to really encourage them. And I think those things are great. From the other point of view, as a mentor, I think the thing that I found was that everybody's different. And you got to really sort of read into how they are and to mentor differently. And especially in the K-12, I've noticed that there are amazing students who just come to you all the time, but they're not the ones who are going to need the mentoring the most. And then so you have to kind of go and identify the ones who are not coming for questions, asking to come for mentoring, but identify those people and then really trying to see how to get them to open up and then to explore themselves a little bit more. Those are the things that I've so far learned, and I'm still learning how to do so. Sally?
Back there, Sally.
I was wondering what advice you would give students, freshmen, who are working with that kind of information.
It doesn't matter. for me, what I always, my advice always is for people to follow your passion. Find out what it is that you're so excited about that you can't sleep at night. You can't wait till first thing in the morning to work on that. And so that to me is, I fell in love with molecules, and I've never had much time to look back. And so that's always my first advice. Besides that, when I accept students into I get about 40 applicants a year, people that are already accepted MIT for applications into my group. And what I look for, and I accept about 2 to 3, what I look for are people that are really good at something. I don't really care if they're really good at engineering or physics or biology, but just really good, shown a very good track record, and then have this great interest to get into, whatever the field, like what they say. I really want to work on engineering, biology to make materials. And then the other thing I look for is this sounds kind of strange, but humility, because someone that's willing to admit they know nothing about something and learn it from scratch. And so I really like that, to get to go in. I really know nothing about batteries, but then they get in there and they learn that. So I think it's that drive, it's that passion that I recommend. I really don't think it's, my degree is in creative studies. People have never heard of that, and they're actually getting rid of my degree, I think. So I don't know if it really matters that much what you major in. I just don't think, I think there's lots of different paths to the same place. And I think getting caught up in all those details, at least from my point of view, as you had mentioned before, you had all these different things that you're interested in, doesn't matter as much as just being really good at what you do and being passionate.
Yeah, I think ditto. But one small thing to add might be that sort of the learning how to learn information well might be the best thing to do in college. So things like, if you learn to not pay attention to lectures in high school, like something I actually taught myself in high school not to pay attention, because that was cool to do that, like sit in the back and then just like chat up with friends and make fun of those geeks in the front. Kind of things. I got way too good at it, and then I've really lost out. I felt like, what you can really learn in college is to learn or to relearn how to really pay attention to how to learn new information. And as long as you are really good at that, you can pick up whatever the information later. It doesn't matter what you might major in. You can major in English and then become an engineer at the end. You can major in engineering, you can become a politician at the end. So I think it's not about what, but how.
Yes. In the back? You. Yeah.
You're both really good at what you do, and from what I gathered from Dr. Matsuda is that you were not very good at the biological. Is there a way that your paths would converge and then you come up with a really good thing?
I think she is very good at the biology. I think that the biology has some trickier parts in the fact that it's hard when you're putting it into a human. But I would like to look into self-assembling electrodes for the brain, so that way you don't actually have to do something that's pull apart the skin. Maybe you can send it in and have them assemble at the surface. So I think that would be interesting.
So there's a chance.
I know I'm not going to play her in tennis, so.
Don't know about that these days, but yeah, I think in a way we kind of look at the problems in a very. It seems like it's different, but it's similar. We both are inspired by biology to make better technology. And, she's in the micro scale, and I'm in the macro scale. But, our philosophy is quite similar.
Nick?
So I believe the number of women in engineering about 30 years ago was about 15%. I think today it's about 15%.
Yeah.
The number of minorities have improved a little bit. So what do you think is important to do, and when is the age when girls need to be helped or encouraged to stay in science and engineering, and what can people do about it? Even later when they get into college, what can you do?
Yeah, that's such a good question. And there are these days a lot of publications about that. So they all seem to blame on the image. So if you look at after elementary school, how well girls do in math versus boys, apparently girls are even a little bit better. But then by the time the end of junior year hits, where the puberty hits and boys are interesting and the girls are cute and all those things, then suddenly it's uncool for girls to be good in math and science. And that's the dramatic change. And it really seems that it's not an inherent ability or the intelligence. So that's really where we have to get in. We have to get in the, between 6th through 8th grade to really change that image somehow. There's not the obvious brilliant idea to change that at this moment. But we know at least that's when we need to get in. We need to have more role models that go in there and show that, hey, it's all right. It's still really cool to do this. And it's going to change the world, and then it might be a little bit tough. Maybe people may pick on you for a little bit, but, it doesn't matter. It's just really important. And, yes, I think that's one of the things that needs to happen.
I agree also completely, and it's partly an image. And I'm working on some programs that I don't think are the answer, but the idea to make scientists and engineering cooler through video and through other media. But I think that we live in incredibly interesting times. I mean, we live in times where energy is such a huge topic that, my son is not quite 3 years old, but we have energy conversations all the time. And it's, the kids that come through my lab, they're all interested in solar energy. And but the same thing with the amazing robotics and other kinds of medical applications. The kids that I meet, the ones that are in elementary school and junior high, boys and girls, are interested in these topics, making the world a better place, changing the world. And maybe the world was too easy, or maybe our lives were too easy for a while. But now we have these challenges that are huge, and also in the environment. And kids are so engaged in stepping in. And so I think we need to make they understand that importance. We need to make it cooler. We need to make it more accessible. And at MIT we have quite a few women in engineering, in not as much faculty, but as undergraduates. In material science, one of my departments, both my departments, we have more women than men undergraduates, both in biological engineering and in material science. We lose them in graduate school, and then we lose even more becoming faculty members.
Yeah, that's actually a good point about the biology infusion with engineering. So women somehow, girls want to help other people, like want to become a nurse, want to do all those things, and then those things are now possible by pursuing engineering too. So I think that's another area that is really changing.
We'll take one more question.
No. Yes, I totally agree with you. So I think, so I think for those people who couldn't really hear the questions, I think he is really talking about can't things like and the anatomical system be helped by the nanotechnology to the point that we can pretty much replace the things that degenerate over time with engineered solutions. That's whether that day will come, I don't know, but I think there are lots of fields are going that way. I bet Angela and I have colleagues that we both know a lot about, sort of overlap in our fields. Those people are working on nanotechnology in the neuroscience field. How do we actually place just the right amount of maybe stem cells or some technology, nanotubes, in a spinal cord where the injury occurred? Can we actually fix those things so that instead of having it go like just the way I do it, take it outside, do the processing, and put it back in? But maybe we can actually fix the original problem itself.
And just a couple of lines to add to that. One of the major places that my group is going now is towards self-healing materials. Well, when I first started in this field, like I guess 9 years ago, I had people call me and saying that this would never work. And so what's the next thing? I said self-healing materials. And I actually wanted it for my BlackBerry, because I'm always dropping my BlackBerry and it's breaking. But now people say, well, that's a little bit out there. That's a little bit crazy. But I think that I think it's doable, and I think a combination would be very powerful.
I'd like to thank Angela and Yoki again so much.
Yeah, so I mean, I chose City College because I was new to Southern California, and it had a great reputation as being the best community college. And Santa Barbara's not a bad place to live, so that was very attractive as well. But I really learned a lot more about City College once I really got here. And I focused mostly on the sciences, and what the things that were so amazing about it were the really small class sizes and the complete dedication of the faculty to the students. I also think that the lab experiences that we had were really superior in terms of the kinds of equipment and kind of experiments that we got to do. And then just the one-on-one contact, the mentoring, the encouragement, it really gave me the confidence that anything was possible. I think that the preparation here really gave me a strong fundamental background, and I think that that was the most important. I really learned how to think about problems, and I did it in an environment that was very supportive. Like I said, I could always meet with faculty. We had weekend breakfast sessions where we had breakfast with our biology class and talked about not only what we were working on in lecture and class, but real science and technology that were happening in the journals, and so that was very exciting. So it's a combination of really strong background fundamentals as well as looking to the future.
I mean, to be honest, out of high school, I wanted to play college level tennis. So this was a perfect place to be. It's very competitive, and also the sort of the available things here in terms of, if you wanted to pursue academic side, if you wanted to play sports side, if you wanted to do any of that, it was all available right here. So it was clearly the right place to choose. Yeah, I wish I talked about it today. It really was amazing. I think I was far more prepared than any other sort of city college, community college people when I arrived at Berkeley. The personal attention you get here is nothing like other community colleges, and I was very prepared. I went right to Berkeley. I couldn't believe how easy it was at Berkeley. In things, at times I felt that it was really hard here, so I think it really prepared me. Yeah, some mothers are looking for meanings in life and in ways to learn new information. And my mom was one of those people, very intelligent person, but kind of was missing goals in life. And a lot of moms go through that when their kids are about college age, and then they're suddenly not listening to you anymore. That's what happened. I wasn't listening to her anymore, and then she really needed something else. So, this was a perfect place for her to attend. Again, for somebody like her who had a college degree 20 years ago, it was just a perfect place to come back, pursue. For her, she originally really wanted to do psychology. She has always been interested in child psychology, but at the same time, she wanted to do interior design, and she ended up getting a certificate in that. So, it's really cool to have all these options for anybody in the community. It doesn't matter how old they are. So that was really cool. I just can't believe how many people here have changed my life. So Mike Mellon in mathematics, he really changed my life. Oscar Zavala, he was a counselor. He just advised me in so many great things. When I was down, he was there to cheer me up. When I wasn't sure where to go, he said just the right things to push me in the right direction. That was amazing. My tennis coach, Pat, it's being on a sports team is really tough, and she was great, very, very nurturing. So yeah, and that's just very small set of people, but it's a great place here.